Hello, can you hear me?
Yes, ma'am.
Okay. So we will start with the more formal mathematical introduction to Bayesian. What we have seen so far was more of a philosophical discussion. So today we will go into the mathematics of it. So first thing is we will have something called as prior distribution of the parameter. Just for the sake of convenience and understanding, let me assume that my parameter is discrete. Okay, so parameter takes, so basically any example of discrete parameter? Can you think of some parameter which is discrete? Yes, or am I completely talking in fiction? Hello.
The Poisson parameter, like number of events in a specific interval, that would be discrete.
Poisson parameter is lambda. It is mean. It could be
Yes,
fractional.
ma'am.
It could be fractional.
But Poisson is always discrete.
Random
So,
variable is discrete, but
okay. Yes.
parameter is continuous. Lambda can take any value. Yes, what about others? Any example of discrete parameter have you come across?
I mean, binomial n comma p n would be a discrete
Correct,
parameter.
correct. So, in binomial NP, n has to be discrete. So, we are not completely talking in fiction. I start with discrete because it's easy to understand with the discrete scenario. So, suppose theta is a discrete parameter with theta 1, theta 2 up to theta k as a set of possible values. Okay, theta 1, theta 2, theta k as a set of possible values of theta. Okay, and of course with the corresponding probabilities, p of theta 1, p of theta 2, etc. Okay, now let x1, x2, xn be a sample coming from, okay, let me simplify even this. Let me have only one observation. Okay, not even entire sample. Let x, so can you still hear me?
Yes, ma'am.
Okay, so these are set of possible values of theta with corresponding probabilities as p of theta 1, p of theta 2, etc. So p of theta I basically gives PMF at theta I. Okay, and let x be an observation coming from some distribution whose parameter is theta. Okay, x be an observation coming from some distribution whose parameter is theta. What we are saying is this quantity is nothing but my prior distribution, correct? This p of theta 1, theta 2, this is my prior distribution, and this is my usual distribution that we always talk about. Okay, this we are always talking about. This is something new. This we have in even in the classical setup, correct? And now what we are interested is posterior distribution of theta. So how does our understanding of theta change after looking at the data? So posterior distribution of the parameter theta would be P of theta given this particular observed value of x. Because theta is having possible values as theta 1, theta 2, theta k, ideally my posterior distribution also would be computed for every theta I, correct? So I would calculate this as some sort of joint distribution of theta I and x divided by marginal distribution of x, because this posterior is conditional of theta I given x by your usual conditional probabilities would be joint upon marginal of thing which is in the conditioning part. Okay, so and joint distribution of theta and x I don't know directly, so I would write it as, how would I write it? I would write it as conditional distribution into some marginal, but of course I cannot write this same conditional because that is what I am trying to compute. So I would write it as conditional distribution of x given theta I into marginal of theta I, correct, divided by marginal of x. So remember, so far we have always been calling this part as the marginal distribution. So far in the classical setup, whenever we said that we knew distribution of x, what we actually knew was conditional distribution of x given that particular value of the parameter. Are you getting the difference? We always said what we have is distribution of x, but that was actually conditional on the given value of theta. So in the Bayesian setup, I won't call it marginal of x, I would call it as conditional distribution of x for that particular value of theta. So if I want marginal distribution of x, I have to integrate joint distribution over theta. That's what you have seen, right? Marginal can be obtained by integrating joint with respect to the other thing, correct? So here, because my theta is discrete, it would be sum over j going from 1 to k f of x given theta I into p of theta I. Is everyone with me so far? This is important.
Yes, ma'am.
Okay, so this becomes my posterior distribution. Now let us introduce the slight complication. So instead of single x, if suppose I had x1, x2, xn, then instead of f of x given theta I would have to write f of x1, x2, xn given theta I. Because xi's are IID, this would become product over I going from 1 to n. I should not use I, j is already used. Say product over L. Okay, product over L going from 1 to n, f of xi, sorry, f of xl given theta I, and this is nothing but your likelihood of x1, x2, xn, comma theta I, correct? So what I would say is my p theta I given x, if I had multiple observations, would actually be likelihood of x1, x2, now x is a vector because x1, x2, xn I can denote by x vector, x1, x2, xn into prior of theta I. Of course, this likelihood also depends on theta I, divided by sum of the same quantity. So, sum of likelihood into prior, where sum is over all possible values of theta. Okay, so far? Now, if my theta had been continuous, the only change that I would make is, instead of calling it P, I could possibly call it some other thing. So, I would call it as, say, G theta given x will be likelihood of x1, x2, xn, comma, observed value of whatever theta I mean this theta whose probability I am trying to compute, into f theta divided by integral with respect to all possible values of theta, likelihood of x1, x2, xn, theta, f theta, d theta. Okay, this is just a continuous analog of whatever we have written here. Now, can I say from these two equations, can I say that posterior is proportional to prior? I should not call this f, I should call this something else, g, because f I am using for distribution of the data. Okay, so prior into likelihood, can I say posterior is proportional to prior into likelihood? What I have is, this part is my prior, okay, and this part is my likelihood. So, I am saying posterior is proportional to prior into likelihood, which means that I am basically ignoring this. Am I allowed to ignore this? That is my question. Am I allowed to ignore this part?
We can ignore it. We are just stating about the likelihood and prior distribution relation with posterior.
Why we can ignore it?
Since we are integrating it, it is a constant.
Constant with respect to?
With respect to
With respect
theta.
parameter theta.
Theta. Okay. See, I am calculating probabilities, or either probabilities or probability density of theta given the data, because in the denominator I have either sum or integration over all possible values of theta, all possible values of theta. So, this is basically constant with respect to theta, correct. So, it is constant with respect to theta, it has no role in deciding probabilities or probability density for theta, and hence I can take it as a proportionality constant over here. Okay, so I can write posterior is proportional to prior into likelihood, and when I write this I am not losing any information, because I know that I can retrieve that constant, I can get that constant by integrating this quantity prior into likelihood. Is it okay? So, this posterior proportional to prior into likelihood is a very key statement in every Bayesian calculation. Okay, so far?
Yes, ma'am.
Now, let us go to one example. We will go to the simplest example. So, Bernoulli. Suppose I have x1, x2, xn as IID Bernoulli random variable with success probability p. Okay. Now, we have to assume some prior for p, and we have to derive posterior for p. Okay. So, what possible priors can I assume? for success probability in Bernoulli setup? Yes. What are the possible priors that I can have? We tried some yesterday.
0 and 1.
0 and 1. What is
Beta
0
A,
and 1?
comma.
Yeah, one prior can be beta A B. This could be one choice of prior. Another? Can I say uniform 0 1?
Yes, ma'am.
Is it okay, Pushkar? Is this what you wanted to say?
Yes, ma'am.
So let me start with this simplest prior. So when I say P is uniform 0 1, what is the prior? Fp is actually 1 if P is between 0 and 1. Okay, equality doesn't really matter. And now we are saying that my posterior is proportional to prior into likelihood. So prior is 1, so I have to just write likelihood. How do I write Bernoulli likelihood? How do I write Bernoulli likelihood? I have x1, x2, xn. So product over I going from 1 to n f of xi is what? Have you never written likelihood of Bernoulli distribution?
We can write as it is binomial which n equal to 1, right?
Yes. See,
So
because
it will
your
be
Bernoulli
P.
PMF you have always written as P and 1 minus P. Sorry, 1 minus P and P. 1 minus P at 0 and 1 at, sorry, P at 1. So I can understand why you are stuck. But think of Bernoulli as binomial with n equal to 1. So this would become P raised to x I and 1 minus P raised to 1 minus xi. The n choose r, whatever part is there, that is gone here because you have only one choice. Is it okay? Does this look correct?
Yes, ma'am.
Because if I put xi equal to 0, this part will become 1, so I will be left with simply 1 minus p, which is what we want. And if I put xi equal to 1, I will have what, p. And if I put any other values of xi, anyway that is not going to happen because my xi's are coming from Bernoulli. So this becomes p raised to summation xi 1 minus p raised to summation of 1 minus xi would become n minus summation xi, correct? So this is p raised to s 1 minus p raised to n minus s if we denote summation xi by s. Okay. So now I am saying in this particular setup my posterior is proportional to p raised to s 1 minus p raised to n minus s. Okay. Does this look familiar? Do you see? Now remember my posterior is distribution of p, correct? So here my p is supposed to be random and this s and n minus s are supposed to be like something like parameters. So have you seen any distribution, any standard in the sense any routine distribution which has this format? Have you seen any other distribution which has this format?
Negative binomial. Not negative binomial. It's okay. So geometry.
You are making the mistake which I expected you would make. Remember, this is distribution of P. So P is not a parameter here. Posterior distribution is supposed to be distribution of P. So when I say you have to locate a distribution of this type, you have to translate in your brain as x raised to something 1 minus x raised to something else. Now does this look like some distribution?
Beta.
Beta. Okay, beta. Are others following what happened just now?
Yes, ma'am.
Yes, ma'am.
We have to remember this is distribution of P. So P is like a random variable. So P is like what we usually consider as x. Okay. So x raised to some constant, 1 minus x raised to some other constant. There may be relationship between constants. We don't care as of now. This is beta. Beta with what parameters? This is beta with what parameters? Then I will write this. Of course, constant we are ignoring because we are anyway writing proportional. So constant would be worked out. So this is beta with what parameters?
Alpha plus 1, beta plus 1.
Alpha plus 1, beta plus 1, correct? Because when you write beta a b, it is something raised to a minus 1, something else raised to b minus 1, correct? So this is beta with alpha plus 1, beta plus 1. So I would say that my posterior distribution of P, which is actually, I can denote it as f of P given x1, x2, xn, is beta with parameters s plus 1, n minus s plus 1. Is it correct? Making sense?
Yes, ma'am.
So we started with prior as uniform, uniform prior with uniform prior for Bernoulli resulted in posterior as beta. Okay. Now if this is my posterior, what is my posterior mean? Because it's a standard distribution, standard means because it's a usual distribution, I know the formula for mean. Mean would be s plus 1 upon s plus 1 plus n minus s plus 1. Am I right? So this would be s plus 1 upon n plus 2. Is it correct? Is it correct?
Yes, ma'am. Yes, ma'am.
So normal scenario, my MLE for P in the Bernoulli setup is S upon N summation xi upon n sample mean, correct? Whereas now the posterior mean is this S plus 1 upon n plus 2. And what is the prior mean? Prior I am taking as uniform 0 1. So its mean is half. So can I say that alpha into s by n plus beta in, sorry, not beta, plus 1 minus alpha into half somehow gives me s plus 1 upon n plus 2. Can I get some values of alpha? Can I have some value of alpha for which this happens? Yes.
Yes, ma'am. We can separate out the alpha terms and then solve
Okay.
it.
So let me try alpha equal to n upon n plus 2. What happens? N upon n plus 2 into s by n plus 1 minus alpha would be 2 upon n plus 2, correct? So 2 upon n plus 2 into half. So this becomes s plus 1 upon n plus 2. This is what we want, right? So with alpha equal to n upon n plus 2, posterior mean is basically a weighted average of MLE and prior mean. Let me repeat. With posterior mean, this is my posterior mean. Posterior mean is basically a weighted average of prior mean and MLE with weight to MLE as n upon n plus 2. Okay. So, when would MLE be contributing a lot? So, when would the importance of MLE be high? If n by n plus 2 goes to 1, correct? Means for high values of n, I can't even erase this, fine. For high values of n, my posterior mean would be more or less be simply MLE. Is it correct? Are you getting what I am saying? Ignore these random lines. Am I connected?
Yes, ma'am.
Yes, ma'am.
Now we have to try another example. So we will now try beta as the prior. Okay. So I will try with beta prior. So let me take P prior for P as beta with say A and B. Now I know already how to write likelihood. So posterior would be prior into likelihood. Posterior would be proportional to prior into likelihood. Prior is, again I can ignore the beta constant from here, so I will write prior as further proportional to P raised to A minus 1, 1 minus P raised to B minus 1. Is it okay? Am I writing it correctly?
Yes, ma'am.
Okay, because this is distribution of P, remember. So P raised to something, 1 minus P raised to something, and likelihood we already have from the top. So likelihood is P raised to S, 1 minus P raised to N minus S, correct? So this is basically P raised to S plus A minus 1 and 1 minus P raised to N minus S plus B minus 1. Okay. So what can I say about the posterior distribution? In this scenario, posterior distribution is again beta, because I am in the same setup with parameters S plus A and N minus S plus B. Okay. Posterior distribution is still beta with S plus A and N minus S plus B as the parameters.
Yes, ma'am.
So what would be posterior mean now? Now the posterior mean would be S plus A upon S plus A plus N minus S plus B. So this is S plus A upon A plus B plus N. Okay. What is the prior mean here? Prior mean is A upon A plus B. MLE is still S upon N. So if I try something like this, alpha into this, 1 minus alpha into this, and I want it to be S plus A upon A plus B plus N. Yes, what should I try? What should be my choice of alpha? Any ideas? Let me try n upon n plus a plus b. If I try this, I would have n upon n plus a plus b into s upon n plus a plus b upon n plus a plus b into a upon a plus b, which is s plus a upon a plus b plus n, which is exactly what we want. So my alpha here is this. So posterior mean is again weighted average of the prior mean and the MLE, with now the weight for MLE as n upon n plus a plus b. So again as n goes to infinity, this weight will go to 1. Okay, because a and b are constants. A and b are constants. They are parameters of the prior distribution. By the way, I don't remember if I mentioned this. Parameters of the prior distribution are called as hyperparameters. Okay, remember the word hyperparameters somewhere. What are hyperparameters? They are parameters of the prior. Okay, now there is something interesting here. We started with prior as beta and we got posterior also as beta. Okay, we started with prior as beta and we got posterior also as beta. So in this type of setup, we say that this is a conjugate prior. Okay, what we say? We say this is conjugate prior. When do we say something is a conjugate prior? If prior and posterior belong to the same family. So here it is beta. Even for normal distribution, if you take prior for mean as normal, the posterior for mean also turns out to be normal. So if prior and posterior belong to the same family, prior and posterior belong to the same family, we call it as conjugate prior. Okay, so beta is a conjugate prior for Bernoulli. Just now we saw it. So beta is a conjugate prior for Bernoulli. Similarly, I told you normal is a conjugate prior for normal if you are talking about mean. Okay, normal is a conjugate prior for normal. And so your homework is to check this, and you have one more homework. Check if beta is a conjugate prior for binomial also. Check whether beta is a conjugate prior for binomial. That is homework. Okay.
Hello, ma'am.
Yes.
Ma'am, this beta is conjugate prior for binomial. This is obvious, right? Because NCX term would be a constant. So
That's
that
fine.
wouldn't come into question.
That's fine. But I want you to write down the proof so that you are comfortable with the
Okay.
derivation.
Yes.
Yeah. So try for normal as well as for this whether these are conjugate priors. Okay. So conjugate prior is one type of prior. There are some other types of priors. Now, sometimes you may not really know much about the data. So in such scenario, how would you about the domain? So in such scenario, how would you choose your prior? So people try to go for what is known as either a flat prior. Okay, so what is a flat prior? So basically the uniform 0 1 prior for P would be a flat prior. Why flat prior? Because we give equal importance to all the values. So it is called as flat prior. so we don't have any preference. Here this makes sense because uniform 0 1 is a proper distribution. But if I am worrying about normal mu sigma square, and if I want prior for mu, and if I say I am going for flat prior, then it becomes a problem, because now my range of mu is minus infinity to plus infinity, and when I say flat prior, it means I want f mu to be equal to some constant. If f mu is equal to some constant and I want that constant to be such that integration over minus infinity to infinity of that constant should be 1, so that is basically impossible. Integration of any constant over the entire real line would actually be infinity. Okay, so in such cases flat prior leads to problem, but still it is an acceptable prior, just that it would be called as improper prior. Okay, it will be called as improper prior. Why improper prior? Because its integration is not 1. Ideally we want integration of PDF to be 1, but here integration is actually infinity, it is not finite, so we call it as improper prior. Is it okay? So flat prior can sometimes lead to improper prior, but people do work with this, okay, because even if your prior is improper, as long as your posterior is having finite integration, things are fine. As long as your posterior can integrate to 1, things are completely alright. Improper prior is acceptable. Okay, so flat prior or improper priors are generally used when you don't know much about data. Some people do call it as non-informative prior, because you are not giving any information about the domain, but some people do object to this word non-informative, because they say that when you are saying that every possible value is equally likely, that itself is information, so you can't really call it as non-informative prior. This is opinion of some people. Okay, so this word has some debates around it. Non-informative prior, flat prior is relatively a safe choice of word. Okay, so today I will stop here. We'll continue this discussion in the next lecture. Thank you.